coming on this session. Let me, until we get these technical issues resolved. In this session, we're going to cover two things. We're going to cover why do we need, I will try to motivate why we need a little bit of, why we care about testing for mobile devices. I'm going to focus mostly on Android, but I will give you a little bit of an overview of the other side, which is basically iOS, what we do. And I will, thank you very much. You did it from the phone. Okay. This is an effort. Actually, we have for DARPA and NIST. We work very closely with them, and we have a startup that was actually spawned from this effort to support testing for mobile devices on various mobile platforms. So part of what I'm going to be talking about is not only best practices, but also the theme is going to be that unfortunately programmers, even if they follow best practices, make mistakes. And what are the state of the art in terms of tools to be able to test your application and make sure basically that whatever you get from either a third party or through your company is being compliant to or not something that you are embarrassed when you put it out in the market. So part of the problem that we're going to be solving and discussing is what is that I need to take. First of all, what is the current state of the art? For example, is an antivirus enough for me to be able to tell if an application is good or bad? Or how do I test a library? And also, Ryan is going to be presenting on the second half of his talk case studies from actual applications that are currently in the market that fail to meet either cryptography or disclosure or even functionality standards. So basically, the apps that we're going to be talking about are very, very popular. I was even dare to say top 200 apps, one of the 200 apps. Yes? Am I?
Yeah, otherwise they cannot.
Okay, I'm sorry. I can put it on.
So we are recording this tutorial.
I think it's okay. It says battery okay. Can you hear me now? Yes. Better? I'm sorry, guys. Thank you. Is it better now? Okay. As I was saying, part of what I'm going to cover is what are the options for application testing, including UI testing, and what are the challenges. But whatever I'm going to be discussing, some of it, although the title says Android, extends to iOS. And I'm going to make sure that you understand when is what. Ryan, as I said, we will discuss about, for example, case studies. We took an app from the market. We have scrubbed hopefully anything that will lead you to find out what is the app about, but we can give individually the information because we don't want to expose a vulnerability that's currently out there in the market to a very big audience. But we will show you how we went through the analysis and what we found. And some of the findings are kind of embarrassing because they are very big companies. But keep in mind what happens right now is that all these big companies, they outsource the development of the code for mobile devices to third parties, and then basically what they get back is not necessarily what they expect. So part of the problem that we're facing is that mobile developers don't care, or companies outsource their tools and the code, and then at the end of the day, they end up getting something back that they cannot test. They can test in terms of functionality, but not in terms of reliability or security. Okay. Why do we care? If you take a look at this graph, it's from Gartner actually, you will find out that the expectation is right now that we will be able to get mobile technologies pretty soon into the mix. So for example, take a look at NFC payment, for instance. That assumes mobile technology. Bring your own device. Bring your own device is at the peak of what the expectations. So, and if you take a look at the x-axis, it's peak of inflated expectations. What that means basically is that people are expecting you to be able to support it, but most people don't. And the reason that we cannot support this is because currently mobile technologies have a little bit outpaced the capability of the companies to go behind. However, as I will show you, it is true that if you ask the CIOs on business, the number 2 ranking in terms of what they want as business priorities as compared to last year is what? They want to do mobile. They want to have their products out there in the mobile. And the number 2 is there because basically you will find out that in terms of security, the ranking is 9. So they want the mobile technologies, but they don't care necessarily to secure them. So what I'm going to be arguing today is by having a set or suite of tools, and that set of tools can potentially enforce best practices when people write code. That's because they have to pass the testing. And I will talk a little bit more about what we do. So the traditional device concerns, we care about eavesdropping, integrity, data exfiltration, denial of service. But this completely changes when we talk about mobile devices. Capture or loss of a device, poor configuration management, automatic updates. Let me ask you a couple of things. When your device comes, you are in a company, right? When you get the device from your provider, who makes sure that the provider gave you the right software? Right now? Nobody. How do you know that when you access the software, this software is necessarily good or bad? For example, do we trust by default Google Apps? I will tell you that when we did the analysis of Google Apps, there are many of them. The example of the game in Microsoft is the same example that I can call for Google. They don't care for every app that they have on the phone. So some of them are not necessarily built securely. So if we take a look at the supply chain, really, on the right side, we have the software, and on the left side, we have the devices. We don't really know anything about Google, AirWatch, Good, ZenPrice, and all of these MDM managers that you put on your phone. And we certainly have very little knowledge about what comes as a hardware. So what we can do is basically take this mix and put it on a pot and try to find out if we can understand what's going on underneath. Like when I build software, can I make sure that basically it's secure based on the fact that I had some testing? So, and how do you do that? And how thorough has to be that testing? And how quickly can you turn around? Is it the only problem that you have testing? And how do you do libraries, for instance? This is what I'm going to be talking about. And actually, at the end of the conversation, as we go through my talk, which is high level at this point, you will see, for example, actual code that you can just put on your phone and the phone will keep crashing. For example, Rahul will give you an example of multi-threading that you can put on a simple application that you can trigger very simply that will make your phone keep rebooting, and you won't be able to stop it. And the reason for that is because we don't check the code. And the reason for that is because Android was never built to be reliable. It was built to be able to be a very quick platform for mobile apps and to sell. And it has succeeded in that regards. But by no means is it a very secure or reliable platform. And the similar things hold for iOS. It's just that we don't have the peering or the open source capabilities to look into that. Now, let me go one step further. What is the state of the art? State of the art is people rely on antivirus code analysis. They perform some sort of static permissions checking. Is their permissions okay? Yeah, sure. Okay, then the application must be okay. Part of the other problems is like functional, static, and dynamic analysis. This is something that's not happening right now, actually, the number 3 bullet. Resource restrictions? No. An app can literally take every single drop of memory on your device or consume the battery on your device without any control at this point. Power metering? No. We don't actually, when you open up your device, how many of you have run out of juice? I run out of juice every day. Do I know what causes that juice to go out? We have absolutely no clue. So you will find out that today we will be talking about power analysis because part of what we need to be talking about is my application creating a problem when it is on a device with other apps or not? And how do an app developer measures it? There are tools. So out of curiosity, how many of you are Android developers? Raise your hand. Okay. You have written at least one application on Android, right? Okay. How many of you have not even seen an Android app code? Okay. That's okay, because we cover, I mean, the design of this talk is to cover all audiences. So basically from people who have no understanding to people who have very deep understanding and help different levels. But keep in mind that progressively we will go from simple to more complicated. Now, what we will cover in this tutorial? We will cover an overview of available mobile analysis. What can I do? So for example, we start and I'm building an app, and I want to make sure that I do the right thing, right? I follow best practices, but still I need someone to check my code. How can I do permissions checking? How can I understand the functional, static, and dynamic analysis, power metering, and resource restriction? And basically, what are, at the end of the day, what the Android versus iOS similarities and differences? And some of them, I have to admit, this talks about the version 6 of the operating system, because we haven't seen yet the next version. But I can show you where the new version is going to basically change a bit things. So so far, what is the big difference between iOS and Android? Do you know? Do we know? In Android, applications are allowed to communicate with each other. In iOS, the applications are running inside a sandbox, and they are not allowed to communicate. However, now this model changes a bit on the new operating system 7. They will try to have multiple tasks that will be allowed to talk to each other. We haven't seen how the model will be happening. I mean, I have an idea from the beta channel, but it's not studied yet. Now, let's talk a little bit more about what else we will cover. Code analysis examples and case studies. I'm going to show you, for instance, user interface testing. How can I perform user interface? Okay, I built something. Can this go into a loop? Can it crash? Does it work for every platform? Can I exercise my application and make sure that, how do I make sure that it looks similar or the same across different platforms? Code examples and case studies. We will have actually examples and case studies from actual app that we will take from the market. Keep in mind, when we talk about analysis here, I'm assuming that you don't have access to the code, the source code necessarily for everything that you have. And certainly this is the case as far as we're concerned for a lot of libraries. So a lot of people build their code, but there is a lot of library code that they rely on that they don't have the source code. We shouldn't be assuming that we have the source code for things. We actually most of the times don't. And I think that the two things that I wanted to cover is multi-threading, JNI, and networking. Networking, I think that most of the people are more familiar, but multi-threading and JNI, which is Java native interface, are two aspects that I want to cover in this tutorial. And actually, Rahul is going to cover them because they are the two major obstacles for reliability. Multi-threading is actually one of the things that can cause the phone to become unstable or the device to become unstable quickly. And the JNI is the Trojan horse where instead of being inside this permission-protected model, the moment that you leave that permission-protected model of Dalvik, you go out to the command line or to the underlying system, other rules apply. And I want people to know about it. And most of the things, and people will ask, but do we need multi-threading? The answer is unfortunately yes, or fortunately, because the UI and what you do on the background have to be able to synchronize. And what about JNI? Do we care about Java native interface? Most of the interesting functionality, including VPN or people who work with operating system, requires Java native interface. You cannot not have Java native interface and create fast code. Who else wants Java native interface? Do we know? Curiously, games. Everything that is geared towards performance, for example, graphics performance, requires access to native interfaces just because they're faster, and Java cannot handle the same way the hardware as the Java network interface can. Part of the problem, and again, feel free to, I wanted to point this out, feel free to stop me with any questions. It's really important not to move on. It doesn't matter, we are very open about any questions that you might have. You can stop me anytime. You can ask, what is this line of code here? Or why do you say that? Anything. I want it to be more interactive. So now we will do an overview of existing security and reliability automated testing tools. So Why mobile testing is difficult? This is actually a very fresh study from Gartner, and I'm borrowing some of their material because I think that they have very good business acumen. So there is a diversity in platforms, OSs, and devices, guys. Right now, you cannot build applications that are going to be even focusing on Android compatible. Do we know why? Why can't you just make an application that runs on everything? The first thing that you will run into is that the graphics, the screen is different. Just because of that, you have a lot of problems. What else is different? The capabilities are different. Some devices have storage in terms of SD cards, some others don't. You have also different operating system versions. You cannot assume that you can just write a code and it will work. I know that that's what people think it happens in mobile space. Actually, in mobile space, because of the diversity of platforms, when you go to upload your application on the market, it shows you which of the mobile devices is going to be running on, but it doesn't tell you if it's going to run well or not. It just tells you if it's compatible. Now, the most popular mobile OS, the Android, is the most fragmented, with 5 major versions corresponding to 9 API sets that had over 1% market share in April 2012. This complexity is compounded by hundreds of different device designs, screen sizes, and form factor variations, such as tablets and handsets. In order to create a template to address that, for each app, you need at least 3,000 lines of code just to be able to tell in which environment you're running. Problems, automation challenges. Sophisticated user experiences involve touch, gestures, GPS location, audio sensors, such as accelerometers, and physical actions, such as touching the handset to near-field communication. What does that mean? It means that a mobile device has much more interaction with sensors. It has much more interaction with the user, something that you cannot easily recreate in an artificial lab environment or using your emulator. How many of you know what your emulator can emulate out of those? Can your emulator understand gestures? No. Can your emulator understand physical actions like, for example, accelerometer input? No. Can your sensor understand, for example, near-field communication? No. So how are you going to test this? You have to have some devices, right? Which devices? Are these devices going to be type A or type B, or what type of devices? The testing becomes very difficult. And also, part of the problem is such interactions cannot be fully scripted or simulated and may involve manual testing on real devices. What we will show you today is that this step can potentially be, in quotes, circumvented a little bit by having a little bit more control of what is being simulated. The third problem is application complexity and sophistication. Mobile devices, for example, have techniques like context, 3D graphics, and gaming. Do you know, for instance, what we use for gaming here in these devices? Are you familiar? Let's say for Android, what would you use? Do you want anybody to venture and answer the question? They use techniques like OpenGL. They have OpenGL library, which is basically fully functional with 3D and everything. Finally, 3 and 4, in terms of OS versions often break applications. Developers have no control. And bug fix latency. Some app stores have a submission latency of 1 to 2 weeks, meaning that bugs cannot be corrected rapidly. See, the market is fast, but unfortunately, fixing the problem is very, very difficult. How many apps do we have currently on markets? Do we know? Combined, more than 1 billion between Android market and iOS. Are all of them tested? Wait and see, I have statistics. Are all of them working? Are all of them permission checked? No. People just write apps. Mobile testing tools and services. Automated tools for testing. I cannot stress that in an environment which is such diverse and so volatile, you need to have automated tests. You cannot expect the to have users that will test your product, and you cannot expect that the developers will do the right thing because you don't know if they will. Instrumentation, monitor, and analytics are part of what you want to do. Best cost practices based on a feedback loop. What you do basically is you develop something, you test it, you find out if it's good, you verify it, and then you go through a loop of fixing the bugs as you go along. Expand to multiple devices through testing on multiple devices and emulators. So for instance, there are design shops out there where you can set your code and you can get back VNC input of how the application will look at different devices. You don't have to buy those devices. There are people who can actually give you that access. And then the question becomes, are you giving out your code to someone who can take it and run with it? We don't know, right? Common failure. UI, power, OS version. Most applications don't work just because they don't work on a device, because the OS version is off, or you try to run it and the UI basically is completely not what you expect. Power. You run the application, within an hour, the phone is dead. People don't run the application again. How many of you have run a game that your phone lasted for an hour and a half just playing that game? I've done it many times. Now, let's go a little bit back. I'm old school. So for the first time when people talked about best practices and things, I wanted to find out if there is malware out there. For the first thing that basically we did was like, okay, I mean, are we talking about a real problem or are we talking about a problem that doesn't exist? Bad code, basically, on the market. So what we did is basically we went to AV vendors and we measured those. I said, let me first try to measure good programs, programs that are out there to protect me, to find out if they have a good design. What we found out is that they drain the battery quickly, cannot be regulated, worse detection capabilities compared to their counterparts, and detection is not guaranteed. Basically, they cannot identify non-pre-classified threats. So I will show you next slide. Some of them call back home and require constant updates, which means the following, that if you put an antivirus on your device or an MDM, you increase the problems because you get security, but you lose reliability, going back to the comments that we have before, because now you have a lot of code from good people that is unreliable. And I will show you how unreliable. So we did a study, okay, of the, we obtained a test set of malware from the wild with 0-day and non-zero day. We downloaded popular AVs from the Android market, some of them paid. We created a cloud system that allows for large scale-up testing. Basically what we did is we put all the antiviruses with a lot of phones on a cloud system, and we kept submitting applications. I will show you the architecture. And we measure the metrics. How many of malware we were able to find out, how much of the applications were crashing, and basically how much of detection latency. Basically efficiency versus timeliness, meaning that how many malicious code we could find immediately and how much it changed over time. Also, we measured how the battery life of the device, given the fact that we added now a new program, right? So you will be surprised to find out, I mean, not really surprised, we know the problem, that some of them had 50% detection or 57% detection within 2 weeks, which increased, but they didn't pick up everything. Also, there are more than this guy. Mobile Bot, which is one of the products out there, was downloaded by many, many people, and it detected absolutely nothing. And you know what which one of those products do you think people love? This guy, the Mobile Bot. Do you know why? It never bothers them. They install them, it protects them, and they never get any warnings because it's a very good product. Is it? So this is the placebo effect of AVs, basically. People like software that doesn't bother them, but doesn't necessarily mean that the software that they have works. So people are inclined to get software that operates well while not doing anything. And you will find out that the list is very much bigger. There are a lot of products that they don't even meet the requirements to be considered as part. I mean, 13.5% here is like literally nothing. So that means basically that there is bad code out there. This is how we basically created the system. We have a service where someone can submit an application, and the application can be tested various ways, including AVs, and then basically go through a list of AVs and assess the results and create messages. Why do we believe that such a system is going to become the standard? Because we believe that given the diversity of the devices, being able to have an automated test where someone submits the binary, not your source code, and the application goes through different tests and then you get a result, allows you both to debug the application without revealing what you have done. Any questions? Yes?
So this testing platform
is available. It's available, yes.
for all the applications?
It is. I mean, we have...
How you can have like a general testing, like scenarios for billions of applications?
No. You have to submit an app, and the app goes through that. It doesn't test... we have a feature...
Test what? This scenario. How exactly?
So you give the binary of the application, and it runs it through all of these antiviruses, and it tells you if it finds something or not. This is only for antiviruses. Thank you for asking, but this is only for antiviruses. Yes? Yes, we had a list of, thank you for asking. We have a list of known malware, and this is with a known baseline. So basically what we did is we went out there, Contagio, Blog, different places, they have actual malware. We took the latest version of the malware, like Lookout and all of these guys, and we took 0 day, and then we kept running it for a 2 weeks period, and then tried to see if the results change and how they change between 0 day, and then we kept doing that for a period of a month for 0 days, and then we collected a lot of samples to be able to do this analysis. The idea here is that we wanted to find out if a 0 day survives, right, and how long it survives because between being detected initially or at all, and then how things happen. Curiously that the set of detections are a Venn diagram. They are not all detecting the same things and then they're missing the same things. They overlap and then they have some sort of space. Part of the problem is that when we did that test, there was no polymorphic malware. Right now, in the market, there is a lot of polymorphic malware, which means that there is no signature. All these guys work with signatures, so they might not be able to create a signature. Let me tell you what else they cannot do. They do not detect embedded malware. So for instance, we created our own program, and we put a malicious PDF inside it. A PDF that was detected from the desktop counterpart of the antivirus. So for example, you can craft one from Metasploit that all of them detect. If you take it and you embed it inside the Android application to be opened when the desktop opens up the application, they don't detect it. They cannot detect it. So basically, any malicious threat that you put there to basically affect a desktop computer, they don't pick up. And they don't support any behavior analysis or heuristics. For instance, when the antivirus runs on your desktop, they have behavioral analysis. On your phone, the only thing that the antivirus do is that they check against the malware against the known malicious database hash table, and if it matches, it matches. Now, why do we care about analysis tools? Again, developers may be well-intended, but they do not necessarily understand the mission or the security policy requirements. They make mistakes, and they use third-party libraries and code. I want to point out the third bullet. We have seen a lot of people that were very, very much into security, but they just used other people's code without knowing, including bugs in their code. The Android permission model is neither sound nor complete, which means that you can get away with it. Intentions, reflection, JNI, WebKit, others, we will show you code. Android permissions are enforced inside Dalvik, but not everywhere in the device. JNI gets away with it. 0-day and polymorphic threats remain undetected with current commercial tools. Now, how bad things are? Badly designed and malicious app exist. We analyzed more than 600,000 applications from the Google Android market. I can give you thousands with incorrect or permissive manifest. So, in many cases, the original application is completely benign. You download it, it updates itself from an unknown location, and now it becomes a malware. Another thing that we found out is the application itself as a single application is not malicious, but combined with another application becomes malicious. So just to give you an example, I have an application that connects to the internet, no photos. I have another application that takes photos, and the two of them talk to each other. Automatically, all my photos go to the internet. This is a common path. Hundreds of Trojans. People ask me, who will download these apps? I mean, all of these apps are out there, but people don't download them. We don't care about those. That's not true. We do care about those because people search with them. They're virtual everywhere, and they're two infection vectors. People download things from the web, and they search inside the mobile app market. Most of the top 50 apps are okay. They're badly designed. Actually, Ryan will show you for a big financial application how they hard-coded their cryptographic materials, and you can get the accounts. However, they are not necessarily malware. See, the idea of malware to me is strange. Is it malware when someone designs an application badly and I can get your account? It might not be malware, but you have the same effect, right? You lose credentials. So we will show you, for example, we have another application from a big telecommunications carrier, one of the top 3. And it has problems that we brought it to their attention. By the way, we have done the ethic disclosure of what you are going to be seeing today to the respective companies. If they have fixed the problem or not is not up to us, but they already know about the problems. As I said, mobile software developers make mistakes, collect and store data, transmit the data. They have good intentions, but unfortunately these intentions are undisclosed to the end user. So to give you an example, they claim that our application is secure and we don't store any of your bank information online, right? And then when you do the analysis, you find out that all the account information has been transmitted to their servers. So are you comfortable with having your bank account on someone else's server? I am not. I mean, not only your bank account, your username and password, too, to get into your account. Are you comfortable with that? I'm not. And actually, Ryan will show you how this has been done. Oh, another thing that I'm not comfortable with, when I lose my phone, I don't want someone to be able to replicate this application and be able to get into my accounts just by replicating this application without necessarily requiring my PIN. That's exactly what's going to happen in this case, too. They perform, as I said, functionality without explicit end-user permission. 2 days ago, we found an app in Europe from an Irish bank that required root permission on the phone of the user. Upon more examination, we couldn't find out why this app required root permission, and we found out that it was just badly designed. But it was from a bank, small but bank. We also have the malicious and rogue mobile apps. Apps basically designed to cause damage. Apps that, and actually, again, Ryan is going to analyze some of malicious apps just for your edification. Applications that are designed to basically abuse permissions or abuse the user nativity to basically get access to bank accounts and other information. And they have data siphons, basically attempt to steal device information, or man in the middle. They serve as a proxy, so whatever you do, they keep a record of it. And there are plenty of those out there. I mean, Bad Piggies is one of the known ones. I mean, there are plenty out there, but fortunately not that much in our markets, but it is happening slowly towards our markets. Chinese markets are the first target. What's an example of malicious code? I mean, do you see these 3 lines of code? Do you see them? This application, with these 3 lines of code, you don't have to know what it is. This application does not have internet access. Nonetheless, by adding these 3 lines of code, is allowed to communicate to a website and send information. So I'm asking you, is it a malicious app? It might, right? If the purpose of the app is just to connect to a website and give out my location, and how does it do that? By giving out my IP, the mere connection to a website reveals information for where my device is. These 3 lines basically allow the app to connect to the internet without necessarily the explicit user permission or even permission for internet. That goes back to the Android model not being complete. Let me show you another one. This is a bank. Take a look. US Bank, Valley Credit Union, Wachovia, Washington Mutual, Wells Fargo, all of these guys. All of these guys this is a bank aggregator type of app. Look at what the user says. We give it 1 star because no bank info would load, willing to try again once the issue has been resolved. All these people who go to this bank are being scammed because this is an application that just takes your data without doing anything. And users are willing to go back and try again because they think that they will fix it. They put a trust that the application that's on the market is trustworthy, and something is wrong with the app because people have not designed it well, but we will come back and check it out again. Twitchy, buttons too small for fingers, keeps telling you to reload. They cannot even understand that the app is fake by the mere fact that it's not even working. So imagine a working app which steals the data. It's OK because it works and does what it does. What we will be talking about is functional analysis. Basically, Android-specific analysis that includes analysis of the application security manifest. What do you care when you download an app? I want to ask you, what do you care about? I personally care to know what the app does. If the app is doing things that I don't want to be doing, then, and what is the context, right? Sending an SMS message when? Or connecting to a website when? Can it update itself? So what we have designed for DARPA and NIST, and in general, is the capability to identify the context. So basically, I can tell you that your application is connected to the internet under these conditions, and it goes there, and being able to download things from this. Actually, Ryan is going to show you reports from actual apps from the market. Coverage. Can I find out what the application does, or do I do only what is accessible through UI? You will find out, we found out that there are apps out there with booby traps, either waiting for an event to happen to be triggered, or just merely by uploading or downloading something, you can make the app do something. In our case, we exercise all the paths, and we don't need the source code for that. We do it on the binary. That includes third-party Java and native libraries, which is really important because when you have an app, it's not just the code of the developer. It's also the code that's been called by the developer, which is the Java libraries plus the native libraries. Finally, we need an application testing framework and the capability to modify the Android engine to enable dynamic policies. Let me give you an example. You have an application that's a game, and you want to be able to remove the application permissions that the application developer suggested and put yours. To give you an example, you want to play a game, but you don't want that game to connect to the internet at all. But you still want to play that game. Right now, the Android model gives you 2 options. One is to say, I accept, and with that you accept the internet connection, or decline and you don't get the application. There's a third option, to say, I accept and restrict that specific application from ever accessing the internet by modifying policies in the Dalvik engine to prevent that app from ever getting access to the internet. And how do you do that? We are all developers, right? You report to the app that the phone is in airport mode always for that specific app without crashing its code. The good part about the mobile apps is that they're designed to be able to handle that type of situations by nature, by the underlying APIs. So you can restrict, for instance, you have an application that requires access to the camera or allows access to the camera. You can always report to that app that another app is currently having the camera, and you cannot get the camera. And the app will never be able to get access to the camera unless you allow it. So there are ways through the Dalvik engine of, without crashing the code and without permitting the code, to still get away with restricting the permissions of what you give for resources. Let me show you, for example, an instance. This is from an app that we have analyzed. Look at what's going on here. On the left, you have the requested permissions. The app requires all of these permissions. Upon analyzing the code, we find out that there are missing permissions. Basically, there are functions that can call to read the contacts, broadcasts, and they have extra permissions too. So you have permissions that are not there, and permissions that are there that are not required. For example, there is no need for here to have permissions to read the logs. And based on the functionality, so remember, when someone submits an Android application, what they claim that the application requires, what the actual functionality of the application requires are two different sets. So here on the right, you find out that the list of permissions based on the functionality are completely different. And some of them, and why would you want to make these two equal, right? Because on one hand, you might have functionality that crashes the application just because it doesn't have it. On the other hand, you might have application functionality that allows code to do things that you potentially not want to do that. So basically, you increase the attack surface without reason. So this is a very simple example of an application that fails the static analysis. In terms of dynamic analysis, you also find out, for instance, that there are applications, this is from a malware, where you not only find out where the code for SMS message has been invoked, but you also find out what is the phone number that they have hard-coded, and if it's a premium number. This allows you basically to debug your code and find out if a library that you have brings in something like this, and basically it's booby-trapped. And the pointer to the SMS message. All of that will become more clear when Ryan presents, because I'm giving a very high level. Also, we found out that collecting metadata of the actual application on the market is very important. We found out, for instance, that developers who are coming from top applications are less inclined to make mistakes, and they're more inclined to fix them quickly. Whereas if you have applications that come from people who just submit applications for fun, they are more volatile and they don't fix themselves necessarily. So take a look at what you can get from an app. You can get the application. You can get who designed the application, what is his website, the features, the keywords. This actually, and the list of permissions reported. If this list of permissions here are not what you see in the functionality, automatically you know that something might be off. Now, this is public information, and you can actually create a database where it has that. Interesting things happen because not many the problem is that when we download mobile apps, we don't have companies like Microsoft or big names behind those apps. We have people that we have never met before. Most of the banking apps are developed by third-party developers that we have never heard before. Now, I will talk a little bit about iOS. What are the challenges for iOS? We can still do testing, by the way. People say that you cannot do testing on iOS. I disagree. You can still do testing. And we have a very big vendor, I would say top 3 Fortune 500, where we did analysis of their app only on binary, and we found interesting things. But still, you can do all of those. You can find out if the communication might be encrypted or not. You can analyze each one of these objectives, HTML, and analysis requirements. Basically, the challenge is that you need data integrity and compliance, and you need to do that when you don't have the binary. You will find out that even in iOS, how do you do analysis on iOS? You have to do it on the device, and you can basically instrument the underlying operating system to get all the calls that you need to do the analysis. You don't have the same freedom as in Android, but you still do things. And one of those, for instance, is the capability to bypass device and data encryption. Yes, your iOS is not encrypted. People can just read your data. Automation of extraction process from a binary, static analysis, dynamic analysis, and implementation and integration of customer requirements, which means basically another problem that we face with analysis is what do you want to include? And that's the problem. I'm not going to go through a lot. I think that Ryan will come up now and continue. I will interject and continue from here after Ryan finishes. Thank you. Ryan, you're on. Put it in your pocket.
Do I just put it on my...
Yeah.
Hello, everyone. My name is Ryan Johnson, and I'm a PhD student at George Mason University, and Angelos is my advisor. So I'm going to be giving a presentation about safe coding practices leveraging a suite of Android application analysis tools. So to begin with, the motivation behind it is just the growing influence of mobile applications, the market. This slide kind of got messed up, but there's right now, as of February, 800,000 applications on Google Play, formerly Android Market. So here are some of the tools that I've written that can help develop or help inform the developer for safe coding practices, and all of these work on the binary of the application and don't require any source code. So, okay.
It doesn't like his shirts. Try now.
Okay.
No, it's fine. It's fine.
Is it? Okay. So first, going to talk about a tool that does static analysis. Essentially, takes the application, enumerates all the API calls, traverses all of the files, and there's a mapping between API calls and permissions, and then essentially tells you whether your app is under-permissioned, over-permissioned, or has the correct permission set. There's also a tool called Intensify, which kind of looks at the use of intents, so that's an application, whether it's going to talk to other applications or interact with the operating system. There's also a dynamic analysis tool, which is uses forced path execution, which executes in a custom emulator and doesn't use the emulator provided by the Android SDK. And most of what that does is it will give you the actual parameter values to sensitive API calls. And then there's also a few case studies of prominent mobile applications. So for Android permissions, there's a permission model for Android. So the developer will request what permissions the application will use through the Android manifest.xml file. So users may or may not actually truly understand what those permissions mean, or what API calls, what functionality they correspond to. And when you install an app, it's done, it shows the user the permissions, and it's done on an all or nothing basis, so you just have to install it or not. And the permission set stays the same after you install it. So talking about the Android API a little bit, for some of the calls, it won't actually tell you that the permission is required, and then you'll probably just find out when your application crashes. And then if you look at the log, a lot of the times it'll tell you that you need a specific permission. And so there's a mapping that was released by some researchers at Berkeley that was pretty complete, and that was a few years ago. And there's a more recent one, I believe, by University of Toronto. The tool is called P-Scout, and it can take any release of the Android OS, use the tool on it, and find the mapping. Okay, so the way the static tool works, so it'll go through the manifest file, look at all the permissions that are requested, and as well as some of the constants that are used for broadcast receivers, because some of those you will need a permission. And so it utilizes the mapping that have been released by other researchers. So it also looks at intents, some certain constants. You have to get the context, generally you have to go through a content provider and query it. So the way it does it, after looking at the manifest, there's this tool called APK tool, which really just uses back Smalley as a wrapper kind of around back Smalley, and then also decodes the resources. But if you run an APK through that, you will get the Smalley files, which essentially a Smalley file generally corresponds to a single Java file, although for nested classes, they're generally in a different Smalley file. So, and with those, you can see all the API calls and the constants. So essentially parse out all the API calls through all the files, and then check the permissions and see if each of those API calls has the corresponding permissions, or at least the sensitive ones. So just record the discrepancy between any that are missing. And there can be false positives and false negatives. Since it's done statically, sometimes it's difficult to actually tell, depending on how much state you're keeping or how much you're looking into how the call is being used, whether they're reading or writing a certain resource. And there's also dead code, so it may identify something that's unreachable and actually won't be executed on the phone. So here's some of the things that it's looking for: the use of reflection, executing commands, loading any libraries, files, media events, like if it's recording anything, telephony events, whether it's sending text messages, opening sockets, and as well as intents and broadcast receivers to see if it's interacting with other applications and how it's interacting with the OS. So do a little demonstration of the tool. So there's 3 applications here. I believe DTM is a malware application. And this is just printing to the screen, and there's going to be all sorts of tokens, which is for when this is parsed out. But it'll give you essentially every single API call the application makes, where it occurs file-wise, and then also the line number that it occurs on, so you can go and kind of check the context of how the call is happening. So, I mean, you can see here that they're going to get your precise GPS coordinates. So for these calls, it requires the find location, access find location permission. So here are the permissions that the application requested, and based on the analysis, it has all the permissions that it needs, and also up here kind of indicates that it's correctly permissioned. It doesn't have any extra permissions or doesn't have any permissions that it requires. Also shows, so like the get accounts API call will require the get accounts permission, and again it provides the Smalley file as well as the line number, and I can show you a Smalley file just to give you an idea what that looks like. So this is from Facebook, and I believe, so like here would be the constructor, some private methods. Is a call to the superclass, so you can kind of parse this out and transform it. I believe this is in the Jasmine syntax. So again, just all the calls that the application makes, which is... Okay, so essentially I go to when you use APK tool on an APK, there will be a Smalley directory, which essentially contains a directory structure kind of mimicking the way, like the package name, and then, so essentially I'll just recursively traverse through that base directory and go through each Smalley file and identify the method calls and then parse them out to the way that, from the Jasmine syntax to the way you may be used to seeing them. And yes?
Can you show us in the code how you call the static analyzer?
What do you want to see in the code?
Static analysis.
That is the output of the static analysis. What did you want to see? You want to?
The code, not the output from the class. The examine the mission model class.
Yeah.
The code source.
This is something
Like.
that we developed for DARPA, and basically use SERE13 that belongs to the company, and we have basically the capability to analyze. This is a static analysis. This is something similar to dynamic. This code basically what it does is it looks into the assembly level and extracts all API level codes, and then you will be able to, we have another database that basically matches what the APIs require in terms of permission. And then at the end what you get is a set of permissions based on the API text. And we can do that also for libraries.
Yeah, when you include a library, it will be in the Smalley file, so you can actually see any third-party code, because you may just blindly add a jar because you trust it, and then with this you can kind of see exactly what they're calling. So it gives some sort of visibility into the third-party code you're using.
So part of what we try to do is basically show you what can be easily done. This usually runs very quickly, right?
Yeah.
But what is it missing too? So he will talk about, we can pick a lot of things from the static analysis.
Sure.
But we cannot pick self-modifying code or
Yeah.
code that is being generated on the fly
No, I
when you
understand.
connect something yourself. That, for that, dynamic analysis is going to be useful. So whatever you see now here, the static analysis is a quick test, right? If it picks something, you know that something is there. If it doesn't pick something, it doesn't necessarily mean that there's nothing. But it will give you a bit of an understanding of what is being used.
Yeah, so I mean, just for example, also it groups some of the calls into the categories mentioned. So basically this, so you can see that it sends a text message and creates a text message from a byte array. So just quickly running the analysis, you can see, and probably just from looking at the manifest, you could tell that it has the send SMS permission, but it may not use it. So this, it actually shows that.
Yeah, also notice that not only the static analysis tells you if something happens, it tells you also where in the code it happens. Because it's really important to have attribution, right? Because you have a lot of tools that they report something happened, but they don't tell you exactly where in the code it happens. Because it might be the case that you have a code call, but it's in a dead portion of your code, or you have a code call, and it's actually in a live portion of your code, and you need actually to know where it is. So the fact that you know where in the assembly
Yeah, so if you were developing an application, say in Eclipse, it's constantly building it as you're writing it, so you could just take the APK file, run it through, and see if you need to add or remove any permissions. So it can inform the developer as to the correct permission set based on the actual functionality.
Also, I want to point out that the static analysis is not precise because it can give you things, but it doesn't give you the entire set of things. Why? Because you don't know which of the code that you include as part of your application is actually exercise versus being used. So you might have a very big library that you never use, and as part of this library you might have a lot of code that is dead, really, but require permissions to be compiled and included. And that is being answered by the dynamic analysis, which actually looks at reachability of code. And that's why I'm saying that you will see two sets of analysis. You will see a static analysis, you will see dynamic analysis, and you will see power analysis, because power cannot be caught by static or dynamic analysis of code because you don't know the footprint of the power based on the code, right? You need a different type of analysis. So part of what we're going to show you is how you do the three sets: static, dynamic, and power. The static analysis covers API calls and permissions, and it covers also the capability to identify if something is hard-coded there, but it doesn't give you full-proof version of what is being called because you never run the code. You just run through it, right? I mean, it's a problem. It's a good first filter, but it's not necessarily the best answer.
So here's an application that requests the internet permission, and this says that it does not use it, because if you look at the call, WebView load URL, that's the one Angelos pointed out where you don't actually need a permission, and it's a way you can actually leak data. So if you obtain some sort of information like location information from the phone, or look at their contacts.
So what he's showing is the opposite. He's showing now a failure of the permission of Android. So we believe that the internet permission should be included. It's not required, but based on the functionality that it does, actually the application does connect to the internet. The functionality is being exposed because now we know that this API should have the internet permission, but it's not included. So in other words, this is a bypassing of permissions for Android, but the analysis still picks it up because it looks at the actual functionality and what it should have. In other words, this application will run without the internet permission, but the mere fact that you pass it to the tester shows you that there's a discrepancy. That's true.
Not just to have the permission.
Correct. That's exactly what it does. Basically, it gives you a baseline for your developer to understand, am I including the right set of permissions, or am I including something that shouldn't be there?
So yeah, you can put beyond the URL extra data at the end. So you can put, a few fields, which I've seen some apps do.
Do you have any malicious app to show? I think we have one malicious, right?
I believe DTM does something. I mean, I think Kim also as well. Let's see.
So see, for example, here we have get accounts, okay? So this get accounts permission, it has very specific requirement. Or GPS is basically access course location. Go down. Also, you see here basically that it gets the device ID, which is basically your IMEI, and it sends it out. Usually when an application gets your IMEI, it's not a good, because they should be getting your IMEI, because it's a unique identification for your device. So you can see, for example, basic things, right? If there's an API that reads your IMEI, something might not, and without requirement, it's a context. It might be an application that does require your IMEI to function, but it's the context of which the application performs that you need to be careful.
So the next program I'm going to talk about, it's called Intensify. So this really looks at an application's use of intents. So intent is an object that Android applications can use to request resources from the operating system, or to you can pass the intent to another application. And there's also broadcast receivers, which you can send an intent to, so you can listen for certain type of events on the operating system, like when the boot completes. So when the phone loads up, you can receive an intent, which your application can perform some action. Then maybe it starts a service, which will be persistent, and then when certain events happens, you can start an activity and present an interface to the user, or just run the service in the background and do whatever you want. So this program is a little bit different. So it does some static analysis, and then it actually does some sort of emulation of the code to try and resolve the action string that's being used in the URI or the class. So there's two different types of intents. There's explicit intents and implicit intents. And implicit intents are where you use an action string, which, say, for a broadcast receiver or an activity, you have an intent filter and you provide a string there. So you could send an intent with that string, and that will go to that activity. Although if there's another activity in another application with that same string, it presents a collision, and then the user has to choose which application should receive it, and they may not have an idea which application should actually run it. So two of the main issues that this looks at is unprotected components. So there's the ability to have one application start an application component, such as an activity, not just the launcher activity of an application, but any activity, any service, or any broadcast receiver, assuming that they're not protected. There's a way you can not export them. There's a tag you can put in the manifest. It's called exported. So if you put exported equals to false, then no application will be able to, outside of your own application, will be able to start it. And
Why do we care about those? The reason is because you can have applications colluding. You can have more than one application on your phone, and they can collude to create a situation where the permission model does not fall across the application. So in other words, you can have data flow generated by one application going to another application and then basically execute. This type of analysis assumes many apps being tested, and it's a combinatory testing in essence, trying to match data flows from one app to another. And part of the problem that we have here, this type of attack is not visible currently on the current version of iOS, because each app is running on its own. It will become very interesting to see what is going to happen on 7, which they will allow. It's basically the application are not going to be running necessarily as app.
so, and the hijacking is where there is a collision. If you are using an implicit intent, which just has the action string, instead of the explicit intent, which has the fully qualified class name, then there's a possibility for a collision. And if other applications if you look at the manifest of another application, you can see the action strings that they're using, and then try and harvest applications or provide a bunch of receivers that will have those same action strings. So if the user chooses wrong, then they can receive that intent, and intents can carry data, so any data that's in there would be leaked. Yeah, so this is kind of just what I talked about. So in the manifest, if exported is equal to true, then another application can start that component externally from their own application. So, and if you don't have, I believe the way it is now is if you have an intent filter for any component, it will export it by default. So you would want to put exported equals to false if you don't want an application to exercise that portion of your code or that component. So, I mean, maybe in some cases you do, but in others you wouldn't. So there's two ways to fix it. Essentially is setting exported to false, and another way is using custom permissions. So you can declare your own permissions in Android, and then you can also set a level or like for it. So I think normal, other applications would be able to get it. Maybe dangerous, I think they have to ask the user, which the user may not really have a good idea about what that permission corresponds to or what that means. And then there's signature and system, which means other applications will not be able to launch it. So the hijacking is essentially when there's a collision and then it relies on the user to select the correct activity to receive the intent. And you should usually, I mean, if it's your own code, you'll know exactly what you're trying to call. So you just provide the class name instead of the action string. And you can use custom permissions. And also there's another issue. So when there's broadcast receivers, sometimes you can have a broadcast receiver receive certain types of events from the OS, like when there's a package installed, when it boots up, when the user's away, when it receives an SMS message. So when there is a broadcast receiver like that, you should check to see what the intent, what the action string on the intent is to be able to handle it, so that other users won't be able to try and exercise that code, even if it's not an actual intent from the operating system. So this, it really depends on what your application is. It may not really be that big of a deal. If you are working with any sensitive data or personal information, you certainly would want to not be able to have another application start one of your components. Okay, so this is kind of how it works. So it uses APK tool to disassemble the classes.dex file into a bunch of smally files. And then what it's looking for is intent creation. So anytime you create an intent, it essentially searches, and once it finds intent creation, then it will start to execute kind of in a custom emulator. And it will execute the code and follow all method calls until the intent is either sent or it returns from that initial method and it doesn't get sent, and then it will just return. Or if it's stored in an instance variable or a static variable, it will, in the program, store it there. And then it will continue through the code and then look to see where that's accessed, retrieve that, and then start executing from there. And also if there's, say, like an intent that has an action string, and that action string isn't provided in that same method where the intent is created, it will find all the methods that call that method and then start executing from there. So it'll backtrack looking for that parameter to find it and then start executing. And also parses out the Android manifest.xml file to look at the tags for each component to see if it's exported or not, or to see if it's protected by a custom permission. So this is kind of just what I just said. Yeah, it also looks at intent filters to look at the action strings that are used. And so do a demonstration of this code. This code tends to work pretty quick too. So this is the DTM app that was just run. So here's some intent misuse. So it's an unprotected receiver. So it has exported set to true, so that other people will be able to send things to that receiver, even not from that application, but from a different application, and kind of just throw an intent to it, maybe put some data in there, and see what it will do, because it will perform some code or do some execution If it doesn't check to see where exactly it's from, the originating source, then it may think it's from its own application and perform some activity. So here's an example of an explicit intent. So this, they actually provide the full class name, and they use a pending intent and use set repeating to call it. Here they use another explicit intent. And here you can include a URI in an intent, so you can see here that there's some website. And you can also include a bundle, which is essentially a data structure to pass data from one component to another. And I think the underlying implementation of it is just a hash map, so it's just key value pairs, so you can put any type of objects or data structures in there that you want. And it also shows the line number and the file, so you can go and look and see exactly where that is being called. So here there's another unprotected receiver. So it's just essentially being exported as exported equal to true, so other applications will be able to call it. And receivers can be registered statically or dynamically. Statically, it would be through the manifest. And then there's also a register receiver call where you can kind of, in your code, once it starts executing, register a receiver. So this one interacts with the operating system. So it will, when the application boots up, it will receive an intent, essentially telling the receiver that the phone has booted up. So at that point, it can perform some actions. And then here they're using explicit intents, show essentially the class name of it. And then this is one just interacting with the operating system. So this is what I've spent most of my time on, actually. The other things were fairly quick to write. So this essentially is a framework to enumerate the different execution paths through an Android application. And it runs in a custom emulator. And you don't actually require any source code. It operates, you just give it an APK file. And kind of the main output that it gives is parameter values to sensitive API calls. So if they're sending a text message, you'll be able to see the number and the message. There's also control flow graphs and call graphs for each application component. So there's, in certain malware, there may be certain conditions that the program is waiting for before it just executes. It may not just immediately execute the code. It may be, targeting somebody in a certain country or waiting for a certain time or looking for a certain file. So if you're testing that, you may not necessarily be able to hit those conditions. So essentially it will model the execution of the application and essentially force it down different paths and record the paths that it has traversed down so that it doesn't go down the same path twice. So kind of if you were looking statically at the code or looking at Smalley, maybe you see a method where there's command execution, but it doesn't show the command immediately in that method. So you would have to kind of traverse back and find where it is. So this kind of lets you see the parameter values, because it may be something innocuous. It may just be top, or it could be SU. So it really depends. So there's about 496 API calls that are being logged. And some of the things we log are reflection, because some people may actually try and hide the API call that they're using. So this is a way kind of, to use reflection, you kind of need to build it up over a series of API calls. Command execution, any network I/O, JNI calls, file I/O, media events, things that happen on the telephone, like when they're sending a text message or getting your Android ID, any crypto stuff, any libraries it's loading, content provider access, like if they're going to look at your contacts, they'll have to go through a content provider, sending intent, so what it's communicating with, and your location, also NFC and Bluetooth. So I've noticed some applications may have some permissions and they may look pretty bad. So if you see an application with send SMS, that certainly warrants some suspicion. But I did see one application where all it did was send you a thank you text message for downloading it and not do anything else. And then the internet permission, that can be just used to get dynamic data from the application developer's website, or it could be used to download a binary and execute it. And over on the right, there's a picture. I believe this is from Facebook, and it's just part of the permissions. So they certainly have a lot of access to your data. So here's kind of the process for how it works. Using backsmalley to convert to Smalley files. Like I don't use APK tool for it because it seems to lose some of the files when you use it. Not the Smalley files, but any certain files. Like if it's not, it'll maintain everything in the assets folder, but if you create like a directory structure and try and load some resource using a URL class loader, that will disappear. So looking up at the Smalley code, there's the Dalvik instructions, and last I checked, there are about 226 of them. So I wrote a Java implementation for each of the instructions and kind of created the whole framework to emulate the way Dalvik operates. It's not stack-based, it's register-based. So kind of when it starts up, it'll parse out all the information about application components from the Android manifest XML file, and then look for the launcher component, start executing that, try and execute, given enough time, all the paths through the application, and record any data that's being sent through intents, and then pass that on to the next application component that's called. And also when it identifies a method call, it will check to see if it has it in the Smalley files and then execute that. It will also check to see if it's if it's not present in that file, if it's present in the superclass file, and kind of traverse the class hierarchy, or if it's in an interface, do the same thing. And the execution, the paths that it's taken are modeled using a binary tree, so like a simple conditional statement, like an if statement, it's either true or false when it's evaluated, the condition, and if it's true, it will jump. If it's not, it just continues execution. So at that point, it's binary, the decision, and any loop essentially is checking that condition and then jumping, and if it's true, then jumping back to the top of the conditional statement and then evaluating it again. So there's a way to model it, and here is just kind of how Java would this for loop in Java and conditional statement would translate into Smalley. I tried to color code the statements, how they correspond. So you can see kind of the system calls in there, some of the hex values that are used, as well as the conditional statement there. It's checking if less than the value in register V0 compared to V2, and then where to jump if it's true or not. And you can see the unconditional jump back up to the top to evaluate the condition again. So we have a large list of sensitive API calls, and when they're actually logged, there's the option to either change the parameters of them or to block them entirely. So like on the analysis framework, it loses some precision because of this, but there's no execution of commands, no setting properties, and also any calls that possibly can block indefinitely aren't allowed to happen. Also can't let it exit the VM or it exits the program. That's got to be messaged internally into the program. And no deleting files. Also for recursion, there's a way where, or at least for reflective calls. So you would invoke a method call, which actually you could call invoke again, and then that could have nested in it another invoke statement, and eventually there would be the actual method call that it's returning. So you can essentially nest them. So check recursively to see what the ultimate target of the call is instead of just letting the first one execute. And for bounding execution, there's a few things that can be done. So you can set a maximum number, like a limit to the number of loop iterations, which also loses precision, but it's also a way to at least execute the portion of the code once, or how many ever arbitrary amount of times you want. You can also let it essentially run as the conditions dictate. Also, you can control recursion, so something doesn't infinitely recurse. Make an attempt to detect infinite loops so it doesn't essentially run forever. And of course, you can't detect that always, so there's a time limit. You can set a time limit so things will actually stop if it does get caught in an infinite loop. And it can also improve performance since that slows things, or it limits things so it's not processing as long. So here's the way registers are represented in the program. So it's just essentially a custom data structure with various fields. Dalvik uses register base, as you saw in the Smalley. So instead of a stack, it uses a register, which is essentially just a reference to an object or a primitive data type. So there are some of the fields in there, like some of the name, the type, the number, the actual object, maybe an object representation of it, like a custom data type that I created for certain classes in Android. Some of the fields, any parameters to it, also the source, so you can kind of tag where the API or the API call that created the whatever object it returns. And also, so here's like a binary tree to model kind of a small x. I believe it's just a single component, but kind of at the top, the root node would be the first conditional statement that's encountered. And I guess if you go left, it essentially it returns from, I believe this is just an activity. So essentially, it'll eventually return from the onCreate method. First, to set up the component, it'll execute the class constructor, then the constructor, and then go into onCreate and start executing the code. So each of the leaf nodes are either when the execution return from onCreate, or there was a system.exit call, or activity finish, or some API call to essentially kill the activity. So there's no user input, obviously. So there's certain things that are done. So when and it's an event-driven OS, so you can see in the code where it's going to register event listeners. So maybe there's something for listening for when the user touches a particular button. And to fulfill that, you need to have an object that essentially fulfills an interface. So if it's something that's listening for onTouch, you would need to associate a button and a class with it, and that class would need to implement onTouch. So anytime anything is registered, it will immediately execute that. And there's all sorts of callback methods, so it will try and mimic the activity lifecycle by forcing it into these methods. So after onCreate finishes, it'll start looking maybe for onStart, and then if that's present, it'll execute it. If it's not, it won't do anything. And then onResume, so to try and get coverage of the code, because there's not actually a user using it. And there's certain API calls which will just return a static value. So when it says get phone number, I mean, it's running on the computer, so I don't have any ability. I don't actually have a phone number, so I just hard-coded some constants for that. And also user input, it could either be random or just some static string like user input. So time for a demonstration of it. So this one's going to take a bit longer, or this is kind of a small application. So
You see that it generates all the control flows inside that application as graphs. But you're zooming in one of them. It can be
So-
much bigger, trust me.
yeah, it can be a lot larger, but this shows kind of the conditional statements and the different paths through the application. So and then also so this is just for a single component. And then there's also a call graph for it, which gets to be kind of large as well. So, and it's also directional, so you can see kind of what's being called from where. And internally, the program has a list of all the methods that were called. So for this application, you can see for like, it creates a URI. You can see the website. And also this is GPS, I believe latitude and longitude that are hard-coded in there. Also parses, it seems to be some sort of sound file. Sends an intent of view using this URL, so it's leaking out your coordinates. Also, it leaks your telephone number, but the way there's a callback for, I believe, on location changed, and that's only executed once, where if it was on the phone, that would actually execute each time your location is changed, and that call is actually before it obtains the telephone number, but you can kind of see down here, or it gets your device ID as well as your line number. And for those things, I just hard code a value. Here you can see that it's getting your latitude and request location update. So anytime, every 0 milliseconds. So essentially every 0 meters. So it's essentially getting updates of your location and getting system services like phone, vibrator. So this essentially, and then these are explicit intents. So this is creating some intent and set repeating. So this is actually going to happen constantly. And it also shows starting this component through start activity. So you can see here the website that you're using, and then I believe this is the hard-coded value that I've used for the IMEI. So you can see where it's connecting, getting device ID, system requesting the phone. One of these might take a little bit. I've limited it to each application component for being 38 seconds, so it's not, it could go a lot longer. But since it's a demonstration, and it generally runs on a server, it's a lot more powerful than this machine. And here you can see the intent filter SMS received. So for this receiver, anytime there's a SMS received on the phone, that will be delivered to this receiver, and then it can perform some action. And I believe for this, it's just to get the message content, your phone number, and then send it out. Also, there's boot completed. So anytime you boot up your phone, this application will know and start running. So it's persistent, and it's, I believe, just harvests all your text messages. So even just looking at the call graph, you can kind of see what it's doing. I mean, this app isn't obfuscated, so you can actually infer some meaning out of the method call names, such as download text or open HTTP connection. Set request. And here you can actually see that they connect. And then there's some timer tasks, so they could be creating some sort of code to run at certain intervals. Yeah. Can you repeat that? Yeah, you can, I mean, through an intent, you can pass a URI, and then you can also pass objects. So you can, there's something Android OS bundle where you can put any object in there you want, and then pass it to another application. So if there are two applications, I believe if they're signed by the same key and like have the same group ID, so say a developer creates two different apps, and then he wants to aggregate the permission set. So maybe you see one application and the permissions aren't look too bad, but then actually when you combine the two, then maybe they have the full power to do all sorts of nasty things. Yeah. So I think one of these was actually a fairly large. something like this where there are a lot of paths through the application. So, and this is kind of a small application, or I guess this component's kind of bigger than most of them, but so I don't think I've hit the root node yet. Wait, hold on. So there is kind of the first conditional statement that would be encountered, and each node at the bottom is either when the component finishes or there's some API call that will kill the program or the activity. So this application actually has another application inside it, and it will, I believe when it runs, it asks you to install the application. I think you do that through an intent. You just provide the URI, and then it provides a dialog for the user. So you can embed an application within another application and ask the user to install it, and it'll still show the permissions and everything like that, so the user can still have an idea of what the functionality of it is. And then this application is actually kind of interesting. It's called adultflix.apk. So some intent usage. And then for this, it'll show, so I believe it's inside the application, and then it writes it to the SD card. So anytime there's some sort of writing, I believe they're just copying it. So it'll show the byte values, and then as well as a string representation of it. And this is the APK, which is actually pretty big, or at least on here. And then you can see it creates some URL object. You can see the URL, and then it connects to it. And parses some URI for your inbox. And queries it. Get originating. I don't think it reached the actual call, but last time I looked at it, it would essentially send a text message out with the contents of your text message as well as your number. I think that was because I was running this with the graph generation, which I wasn't last time, which kind of makes it a bit slower. And this is the application that's embedded in the other application. It's called AdultFlix. It's a pretty small application. Essentially, all it does, I've ran this, and it creates a web view, and it disables the back button, and then it loads this URL on the phone, which will display a web browser. And so it's motherless.com with the search query of Kim Kardashian, and it's a pornographic website. So I wouldn't recommend going there right now, if that's what you guys are thinking.
And I think we should take a break now because it's already 1 hour and 50 minutes.
Okay.
And people are a bit tired. And let's take a break. So when we come back, we continue with the case studies and then some of the other speakers.
Okay, yeah, the case studies are just right after this. Okay.
Let's take a break, guys, because I know that there's a lot of material and the tutorial is a bit fun. So we will continue after the break.
Okay.
Can you put the slides up for the case studies?
So those slides have available CV?
Yeah, we didn't know how many people Okay, the PDF.
I mean, if you prefer the PDF version, the print version, because there are a lot of them. That's why.
PDF, I think.